we talked about the half bridge and full bridge, 50% duty cycle, and we talked a little bit about the pulse width. We can control the pulse width, and we said what's the advantage. We can eliminate some of the harmonics in the system, and it's going to help us with a better THD. We're going to go through one example now. This example is from from the Daniel Hart book, the book you had for ECE125B. That's the example from that book. But let's go through it to get a little bit more familiar with this concept of THD, harmonics, this kind of things we're talking all the time. Let's go through that. I'll give you the first homework, by the end of this week, you will have it, before today is Thursday, right? Tomorrow it's Tuesday. I'll give it to you maybe during the weekend. You will always have at least one week, when they give you homework, you have at least one week to try. This is from your book. You don't need to write it down if you want. Just listen. If you have the book, you don't need to write it down. But let's see what it says. For the inverter in example 8.1. I think it's the full bridge. No, that's the full bridge. Yeah, that's the full bridge inverter, the one we talked about. Yeah. We said we have an inverter, full bridge inverter. Sometimes to make my life easier, just I use this one, If I put this cross here, this, from now on in this. This is that, you see that one across, means the switch with anti-parallel drive. So it says we have a full bridge inverter, VDC, this is a DC bus. It's a VDC is 100 volt, and it's supporting an RL load. This is the output of this inverter, right? We put a load here. Last time as well, you put the load right in the middle. You can bring it here. This is the load we have. There is a RL load. R is 10 ohm, and L is 25 milliamp. This inverter is going to be 60 hertz inverter. What does it mean, 60 hertz inverter? The fundamental of the output AC voltage is 60 hertz, like the what you use in this outlet, right? There are 60 hertz here. So that's what he's talking about, the fundamental. He's not talking about the harmonics, what we have. We said we are going to have a load like this, 60 hertz load. We said that determine the amplitude of the Fourier series term for the square wave load voltage. So we're going to calculate the voltage THD. Let me see, I think I can do it more here. We're going to calculate the voltage THD here, VTHD. I want to know how much is the VTHD, and this is the V, right? And this is the I. And I want to see how much is the ITHD. The perfect case, if the THD is 0, is perfect. Means you have pure sine. Let's just, before going to calculate the THD, let's figure out what's the THD before we start to solve this problem. If we have a waveform in general, let's say f of t, right? Is f1 plus fn sine of n omega t plus n, sorry, phi. This is a system with a harmonics, right? This is a fundamental harmonics, and these are the rest of the harmonics we have. So if we have a system like this, the THD for the F, that's what I call THD. THD is basically going to tell you how much of non unwanted harmonics you have in the system. We're going to talk about this one, kind of representing a percentage of this harmonics in the system. So basically, it's going to be what we have here divided by what we should have, right? If we don't have anything here, it's going to be 0, right? 0%. If it's really bad, this guy is going to be a very, very high number, so it's going to end up a high, number for the THD. But in general, THD is going to be defined not one. And forget the one, the rest of them, and not one. Not one, but the rest of the harmonics we have in the system is going to be is the percentage of this. Basically, this is the maximum value I'm putting here, right? This is the maximum value of F1, maximum value of the nth harmonic. Some people, they use RMS. It is going to be the same. Or you can say here, again, sigma, but not 1. Just get rid of the 1. It's going to be F and RMS to the power of 2 divided by F1 RMS times time. These two definitions are the same. Either you can use the maximum values for both of them, or you can use the RMS values for both of them. Why they are the same thing? Because there is a square root of this one should be divided by a square root of 2, right? And this one should be a square root of 2 again, right? Basically, to the power of 2, a square root is going to be a square root of 2. This one is going to cancel this one, right? My point is these two equations are the same. Either you use the RMS, the maximum value, or the RMS, there is no difference, right? Or we can write it another way also. Also, we can say PhD percentage is going to be, here again we're going to have the F1, but here we're going to have F minus F1 to the power. So the F is this one, right? So if I have a square waveform, right? Look at here. If it's this one, I can calculate the RMS of this one easily, right? I don't have to go through the Fourier series and see how much it is. I can use this one, right? Minus the fundamental. I calculate the fundamental of this one divided by fundamental is going to give you the TH. Put RMS because most of people they do the RMS. They go with the RMS. F1 RMS. Now we know what's the definition of THD. Basically, the lower the THD, the closer we are to the sine wave. The higher THD means the waveform is getting far from the sine waveform. In inverters, we would like to have a perfect sine wave output. That's what we want to have in inverters. But you cannot have that. We can improve that one. We can make it better and better with the different techniques we are using. But never ever you're going to have perfect sine output. Always there's a THD involved. Usually less than 5%. If you put it over the scope, even you cannot see by eye. You think it's a perfect sine wave. When you look at it, you think, oh, it's a perfectly sine wave. But it's still, the THD is 4%, 3%, something like that. Now, it says for this inverter, we have RL load, 10 ohm resistor, 25 millihenry inductor. We have RL load is like this. The DC bus is 100 volt, and this inverter is 60 hertz, inverter. It said calculate the voltage THD and current THD. Why? Are they different in the THD?
Yes, depends on the load, or for an inductive or capacitive circuit.
Why?
Because that affects the waveform.
Yes, because we'll write it down here. So why is asking for both voltage TC and current TC, both of them. So basically, we know this inverter, how the waveform is going to look like. It's going to be like this. This is the V, right? How much is this voltage here? VDC, and how much is it here? Minus VDC, right? 100 minus 100, right? How about the current waveform? I'm plotting during the steady state, right? So basically, if this is the current, this one is based on, this is 60 hertz, most probably, let's say how much is the time constant for this one? How much is the time constant here? Tau is how much? Is L over R or R? Am I right? L over R. So it's going to be 25 divided by 10 is going to be 2.5 millisecond, right? That's 2.5 millisecond. So because it's almost millihertz, right? From here to here is how much? How much is this one? This is 60 hertz system, right? How much is that? Right? 16.167 milliseconds because that's 60 hertz waveform. So how much is this one? This is almost half. This is 8 milliseconds or 8.5, something like that. Right? Now compare with this one. How much is this one? 2.5. That one is 8. It's maybe 3 times, right? A little bit more. If not, if it was 8 times, when I plot this one, I said it's going to be like this, right? Because it's more than 4 times of the time constant. System is going to get to the stable side, right? For the DC circuit, we said if you are more than 5 times of the time constant, you said you are in a steady state, right? Basically, the waveform is going to be like this. But in this case, because it's almost 3 times, I'm guessing it's going to be something like this. I guess it's going to be something like this. And here again, it's going to go like this and like this. And this average should be 0. The one I plotted here is not. I plotted that, but should be 0. Now, can somebody tell me how much is the maximum here? If this one was very long, divided by R, right? If you have a RL circuit like this, right? This will be like something like this. RL VDC, right? I'm saying if this one was very long, right? So when you close this switch, right? At the steady state, the inductor is like short circuit, right? The current in this circuit is going to be VDC over R, right? But this one is not going to get there, So basically, this is 10, and this one is 100. Maybe this one is about 8. So if this is 100, I put here 100. No, sorry, 10. This is a 10 amp. This one is going to be a little bit less than 10 amps, and this is a minus 10 amp, right? Because this one is not getting to the steady state. It needs a little bit more time to go to the steady state, right? But these are not important. These numbers I'm putting here, but just I'm giving kind of feeling about this circuit where we are going to be with the current and voltage. Now we need to calculate we know the Fourier series for this thing, right? What was that? You had this one. We said Vn is going to be I think it was 4 VDC over how much? N pi, right? What's this one? Right? And it has only the odd harmonics, right? N is equal to 1, 3, 5, and go, right? This is a kind of famous waveform. They call it a square wave inverter. This is the simplest inverter you can build. Very, very simple inverter, But how about current harmonics? Can somebody tell me how much is the current harmonics? Let's look at this circuit first. If we have an AC source here, right, and there is a RL here, and this one is a V1. V1, I mean, there's only one harmonic. How much is the current? How much is the current? Just the magnitude of current. I don't care about the phase and those kind of things right now. How much is the magnitude of the current? Right? It's gonna be like. But if I have a third harmonic, I'm not sure, have they ever tested before this one in circuit theory? Usually this is what I like to give the student. I put two sources like this. If I was teaching circuit theory, I would give you a question like this. I said, okay, this is for example, I do 10 sine of 60 hertz, alright, you know, but it's going to be 377 right? And I said, okay, you have another source is for example 5 sine of 3 times of this one, how much is it? I don't know, 1000, whatever. 1000 t, right? Do you know how to calculate this current?
Yeah.
How?
Just use, like in the frequency on the sheet there, and the amplitude on that.
How?
I want the source.
Yeah.
That's right, that's the source, that's right.
So they call it a superposition, you know, theorem, right? So okay, let's get rid of this one. I know how much is the current. It's going to be R and L, right? I know my I is going to be V, this voltage divided by that, right? And the frequency is this one. Now I get rid of this one. I have this one. But when you are going to calculate this one, right? This is how much? 1000, right? So basically your current also has two components. It's going to be something sine of 377 t plus something sine of 1000 t, right? That's the way you solve it. Now here you have a denominator. In the circuit, you know, it's 1, 3, 5, 9, 5, 7, 9, all the way, right? So basically IN is going to be Vn for right, for each of them. If I want to calculate I1, N is in 1, right? It's going to be V1. How much is the V1? 4 VDC over pi. So I'll put it. You can create an Excel sheet, simply a simple Excel sheet. You know, if you calculate this one, you can see after maybe the first 10 harmonics, this one is going to be very, very small number. Say, okay, forget it. You don't need to look at those one anymore. But here in the book, there is a table. You know, just let me go through this table. If we do this one for this example, this is what we're going to do. So I want to put the table here. I'll go this way. Number of harmonics. And after that, we are going to go 1, 5, up to 9. Yeah. 3, 5, 7, and 9. Right. So how much is the frequency? Fn. How much is here for the number 1? 60. How much is for the number 3? 180. 3 times 60, right? The frequency is 3 times, right? How much is for this one? 300. 420. 540. So these are what you can see. There is a 11, 13, 15, 17, but you can see those ones are very, very small. And we're going to ignore them. But if you're going to calculate it simply, you can put the Excel sheet here, put this equation here, just copy paste it, it's going to calculate of whatever you want, you know, quickly. Now, the next one is the Vn. How we are going to calculate Vn? VDC is a 100 volt, pi is a pi, 4 is a 4, and now we are going to put 1, 3, 5, 7, 9 for there, and calculate all this one, right? So if we calculate that one, V1 is going to be 127.3. V3 is going to be 4, V2.4. So look at here. It's not really good. Look at here. The only one we want is this one, right? Right here you can see, but let's forget the rest. This is almost 1/3 of this one, right? This is like 30 each. This is not really good system, no? So if you go to 5, it's going to be 25.5. If you go to 7, it's going to be 18.2. If you go to 9, it's going to be 14.1. You can see this one is getting smaller and smaller. You can go on. Now the next one we're going to calculate is a Zn. You can call this one Zn. Zn is going to be r squared plus nl omega to the power. Right? So Z1 is, how much is R? R is 10 ohm, L is 25 millihenry, omega is going to be based on this frequency. So omega you can say is a 2 pi f, 377, but for first harmonic is 1, for third is 3 times that, 5 times that, you calculate those. So the next one is going to be Zn. So if you calculate this one, for the first harmonic, the impedance is going to be 13.7. For the third harmonic, it's going to be 30 ohm. You can see this one is growing fast. Why? Because there's an n squared here, right? For the third harmonic, it's going to be 9 times than whatever it was before, right? So the next one is going to be 48.2. The next one is going to be 66.2. And the next one is going to be 85.4, right? So we calculated the harmonics of the voltage. We calculated the impedance for each harmonics. How much is it? Now I can calculate my current harmonics, right? How much is IN? Vn over Zn, right? If you look at these two equations, basically IN is a Vn over Zn, right? So we'll go V1 divided by this one is I. V2, Vn divided, V3 divided by Z3 is the I3, right? Let's calculate those ones. So if you go here, it's going to be 9.27 amps. These are all amps. This one is going to be 1.42. Look at here. Compare this one with this one. This is almost 1/3, right? How much is this one? Something about maybe 10%, 12%, 13%, something like this. Is much better, right? You can see already the harmonics of the current looking better than the voltage. Why? Because we have L in this circuit. Remember we said L, we were saying L is a filter, it's going to clean up the current. You can see here what it's doing here also. It's cleaning up the current. So if you go calculate the number 5 is going to be 0.53. And number 7 is going to be 0.27. And number 9 is going to be, see this is almost, it is 0.2, this is 10. It's going to be 2%, right? This one is like 2% of this. We don't need to go further more. So we put this table together here. There's another one I want to put here, but I'll calculate this one a little bit later. I call it Pn. Pn is, how much power we are getting. Every harmonics has some power, right? How we define Pn? It's going to be R. Do I need to write Rn or not? Does it really R care about the frequency or not? No. So basically, it's going to be R In to the power of 2, but RMS. I should put RMS value also, right? This is a resistor, the power is going to be RI RMS to the power of 2. But I said, does this one care about the frequency? Or it does. Not here. We're not going to go through that one here. But when you get to the very high frequencies, like I don't know, kilohertz, 20 kilohertz, we call it Hall effect. You know that, right? If you have a conductor, it's like this. Let's say this is a cross section of conductor. The higher, if you have a DC current is like this. Uniformly, it's going to go through everything, right? The current is going to be uniformly, distributed here and go through all the conductors. But if it's an AC current, if you look at the current, it's going to be like this. Here you are going to have more. They call it a skein effect also. Here we are going to have less. I can bring you one final element in case I did, I modeled this one for an inductor. You can see. So basically, this way, if you look at it, the resistance is going to increase. They call it a skein effect. When you have a high frequency current, the current trends to go through the surface of the conductor. So basically, instead of having all this surface, basically it looks like you have this surface. You know what I'm saying? You have a conductor with this much cross section, right? So this is less than this, right? Basically, and the resistance is L over, I think, what is sigma A, or sigma LA is was here. I can't remember. I think it was like this, right? So basically, in this case, AC current, how much is the A is this area, right? In DC case, A is here, right? So you can see in this case, A is smaller. A is smaller, means the resistor is bigger, right? They call it AC resistance. If you somewhere you hear about the AC resistance, you don't be surprised what's the AC. There's a DC resistance and there's the AC resistance. AC resistance basically is talking about the skin effect and those kind of things, causing to increase the actual resistance of the wire. That's the AC resistance. But for this course, R is not a function of frequency. R is fixed. Okay. So every harmonic is going to give us this much power. So if I'm going to calculate this one, I'm going to put the detail here. How much is going to be this one? P1 is going to be, R is 10 ohm, right? Times, how much is the I1 RMS? How much is the I1 RMS? How much is the RMS value I put here, or is the maximum value? Let me just quickly verify that. This was very handy. These are the max value I have here. So it's going to be this one divided by square root 2. Why I did divided by square root of 2? Because these are maximum, right? To get the RMS value of this current. Divided to the power of 2, basically this one is going to be 429.31. This is for the first harmonic. This is the power is going to be transferred from here to here, right? Almost 500 watts is coming through the first harmonic. This is like a, if we are going to model it, this is like you have a load from here, from this room, you are going to go to the other room, and you have a 10 different, levels. One of them is big and, powerful. One of them is cheap, you know what I'm saying? Think about it, the big one is going to carry the most of the load, right? The little one is going to take a little bit of the load to put it there. This is exactly like here. You can see this one is going to be, if you calculate, this one is going to be 10 watts. If you calculate, this one is going to be 1.4. This one is going to be 0.37. This one is going to be 0.14. See? So usually for the power transfer, we don't count this little one. We say, hey, you're not going to do that much for us. Forget it. We are going to focus on the first harmonic, right? So that's what you do. So you focus on the first harmonic. This is the almost take all the power for you over there. Yes, this guy can do some, but this is the one who does that. More than 98%, 99% of the work, So basically, we ignore this one. We say, this is not. They didn't transfer any power. Right. Now we want to calculate the THD of the voltage and current. So, how much is the voltage THD? Based on that equation I put over there, it's going to be sigma. Let's go, where is the voltage here? It's going to be this one to the power of 2, plus this one to the power of 2, plus this one, right? So it's going to be 42.4 to the power of 2, plus 25.5 to the power of 2, go all the way, divided by, how much? I use the maximum values, right? 127.3 times 100. So if you calculate this from THD is going to be it's going to be 48. You know what's the standard number usually you want? 5%. There's a THD. The lower the better. Don't go wrong way. The lower the better, Yeah, 5%. Usually they want 5%. Think about how bad is this one.
So you're supposed to use max for the THD equation?
You can either use the max, but you should use the max for both of them.
Okay.
Or you can use the RMS for both of them.
Okay.
Yeah. Whatever you use for one of them, you should use the same for the other one. But if you calculate the ITHD, basically you do the same thing. From here, if you calculate this one, ITHD is going to be 16.7%. So almost 1/3 of that, right? You can see the current THC is much better. The good thing is usually when they use the standard, they care more about the current. You know, that's a good thing because the voltage is really difficult to bring it down to 5%. But voltage is easier because when you select a bigger inductor, it's going to help you. You know, let's go solve the same problem we solved here. Make this one 50 milliamp. Just go to this one to see how much is going to. I think this one is going to drop to 9%, something like that. Just double the inductor. See, this one is going to come down. But this is not the right way to do it because inductor also is expensive, it's bulky, it's heavy to add to the circuit. So, but I'm saying one way is to increase the inductor size in the circuit. Is going to help you to reduce the harmonics in the current. If I put even 200 millihenry here, it's not going to affect this one, right? This one is not, doesn't have anything to do with the inductor. Adding inductor is not going to help us here. But what is going to help? Capacitor. If you had a capacitor here, it's going to clean up the voltage a little bit. Any question? You had a question.
What does that 48.3% mean exactly? What does that mean?
So this one is talking about this percentage. Do that here. How much your system is far from the sine waveform.
Okay.
1 is the worst possible, you know?
Yeah.
You know what I'm saying? 0 is the best.
Right.
You are the closest. So you are halfway back.
One eventually equals 0.
Okay. So this is the one example of vector. Now
DC current. Some DC value.
here we didn't control anything. The only way I said you can reduce the harmonics in the system for the current to increase the current, to increase the inductor. But let's go through this example again. Now I'm going to do harmonic elimination. The one I was chopping the voltage, right? The one we had 4 cases. We could have an S1, S1, S4 on, S1, S3 on, S3, S2, and S2 and S4 on. We had 4 cases, right? Let's look at that case. We are going to go through the same example, but with that. And keep this one in mind, because I'm not going to change the DC bus. See, this is what I got in this case, right? When you design, for example, you want to design a simple UPS for home. You can do this one for home if you want. This number, this is not good enough. Why? Because at home, you need how much? Right? So this one is about, I think, 170 volt, right? Something like that. I believe it's 170 volt. So you should select your battery. So you say this one, the first one I want to be 170 volt, right? You put here 170 should be 4 VDC over 1, 4 pi, sorry. So it's going to be how much? 3 up times this one is a 510. 510 divided by 4. How much is it? 510 divided by 4. It's going to be 130 ohms, right? VDC should be almost 130 ohms. Right? If you want to design this inverter for home, you want to build a little UPS at home, right? You should make sure you have at least 130 volt battery here, right? To be able to get how much? 110 volt for the first harmonics. For the first harmonics, keep in mind. This is a simple design. Hey, go design UPS inverter for me. You know, tell me how much battery should I get. You know, I want this much. We'll go through another example. I want this much THC. Tell me what should I do here. You know what I'm saying? So we're gonna start from the first thing. You say, okay, if I'm gonna use this 50%, so at least from this equation, right? The V1 I know how much I want for my V1. How much I want for my V1 at home? 110 volt, right? Everything at home is 110 volt, right? I want 110 volt. So with 110 volt I can calculate how much battery I need, right? You go select this one and you'll go a little bit higher. A little bit higher, not a lot. If you go a lot higher, what's gonna happen? No, you instead of having 110, maybe you have 140 volt. And that way you're going to kill your equipment, right? A little bit, if you design it for 120 is good. Because usually when they say 110, then those equipment they can easily work with 120 or 105. You know, you can design it to be when the full charge, everything is good. You get about 120 because your battery is going to start to discharge, right? So for the full charge, you say, okay, I want to get 120 volt. But when my battery starts to discharge, I don't want to be less than 105 volt, right? This is the battery selection again. When you're going to select the battery, you'll see if it's a lead acid battery, you can see they change a lot, right? But if it's a lithium ion battery, you know it's pretty flat. If it's a flat battery, the charge and discharge doesn't change that much. See, this is a lithium, this is a lead acid battery, this is a full charge, this is a full discharge, right? But if it's a lithium ion, if you start here, it's going to end up a little bit here. A little bit drop here. So if it's a lithium ion, you don't go with that. Because all the time it's very 120 volt. But if it's a lead acid, you should make sure you cover these things, right? But lead acid is cheaper. Again, when you look at it, lead acid battery is much cheaper than the lithium ion battery, right? These are all the design parameters when you start to do something, it's going to come to the equation. Now, we are going to solve the same problem with the harmonic elimination. We are going to get rid of this worst one, right? This is the worst one, right? I'm going to try to get rid of this one in my circuit, you know, in my output. So let's go back to the same example. Before going to the same, yeah, we'll go through this same example. We're going to solve the same example. Let me just make sure 10 on 2.60. Yes. So what he explained in here, this is the ideal example, the next example. He said we have a full bridge inverter with this much R, this much L, and it says, instead of giving us the usually it's not like this, but instead of giving us the DC bus, it says I want to have this much current for my first harmonic, basically matching this number. He said I want to get the same output power, right? How much was the output power here? 430 watts, right? If I have the same fundamental current here, how much power I'm going to have? The same power, right? It's going to be R times that, times this current to the power of 2. Basically, it's trying to compare these two examples. If I want to have the same output power and get rid of the third harmonics, who designed your system? Go, let's calculate it again. The THD of the voltage, THD of the current, how much DC bus I need, how much battery I need, right? So this is the question. Again, this is 60 hertz. We want to have a 9.27 amps, you know, at the output for this. So, and we want to have a V30. We want to eliminate, we call it harmonic elimination. We want to get rid of this third harmonics in this circuit. So what should I do? So we talked about this one. That was again full bridge, but with what kind of output? The output voltage was like this. This is one cycle I put it together, right? This is the alpha. This is the 2 alpha, right? And this is again alpha, alpha, alpha. And this one is 180 degree, right? And this is 360. This is one cycle. The output voltage waveform is like this, right? With the harmonic elimination. Now, what was the equation for the voltage? I think we had this one. We said if we have this one Vn, it's going to be 4 VDC over n pi, I think cosine of n alpha, right? You should have it in your notes, right? So, let's first of all figure out how much is the alpha. This is switching pattern I need to put here, right? So if we call this one S1, S3, S4, S5. So somebody tells me, hey, how should I turn off my switches, right? You have a 2-pulse generator. You need to generate those pulses connected to your gate driver to turn off these switches, right? It tells me, hey, give me a pattern. I can put it on my function generator so to generate this voltage at output. It doesn't have a third harmonics. So I said, okay, so we don't want third harmonics. Let's calculate how much is the V alpha. How much is the alpha, right? How much is the V3 based on this equation? Is going to be 4 VDC, right? Over 3 pi cosine of 3 alpha, right? I don't want third harmonics in my output. So this one should be how much? 0. So this one cannot be 0, right? This one cannot be 0. How much alpha should be?
30 degrees.
30 degrees. So I got this one. Alpha 30 degrees. Right? Now, I want to know how much battery I need. How should I calculate my battery value? Hmm?
The voltage you need because of the power you need.
I know how much I want I need, right? So I can calculate, I can go through this equation here. I can go back and calculate my V1, right? How much is the V1? Right? Z1 I1, right? I'm talking about the magnitude, you know, just not the phase. I'm not talking about those. How much is the Z1? Right? No, there's no capacity. There's no capacity. And I said if you want to clean up the voltage, you put the capacitor there. So how much is I1? I have it here, right? How much is R? Is 10 ohm. How much is L? 0.025, right? How much is omega? 377, right? You put all this number here, so you can calculate your V1. Let me see, let's calculate V1 here. Yes, is yeah, you're right. You didn't have to calculate 127.3. Because it's the same I1, right? That's the same I1 and it's the same Z1, right? So it's going to be 1.27 0.3. But you calculate it here. Now, what should I do next?
Plug into the equation.
To which equation?
For VDC.
Yes. No, not that one.
No, not
To
that
this
one, yeah,
equation.
that one.
To this
Both sides
equation,
of it,
right?
yeah.
So how much is V1? V1 is going to be 4 VDC over 3 pi cosine of alpha, right? And also, sorry? You're right. And also, I know V1 should be how much? 127.3. And this alpha is 30 degrees, right? Just put these two equal. From these two, you can calculate the VDC. How much is the VDC? And 16. See? You got rid of the third harmonics at the cost of what? Higher DC bus, right? See, I am getting the same current output, I am getting the same power output, right? As I say, forget this one. We don't care about this, right? So I have the same input output current, right? So basically, which means the same power. That I'm building an inverter is going to give me almost 500 watts, right? But at what? And I have less harmonics. We're going to calculate those ones. We're going to go again calculate the voltage THT and current THT. Definitely they're going to be better because we're getting rid of the third harmonics, right? But at what cost? Here. See that here? So previously you had 100 volt. Now you have to have 116 volt, right? You need a bigger battery pack. So this is the effect of harmonic substitution. You are losing a little of your DC bus. To compensate for that, you have to bring your DC bus higher, right? To compensate for what you are using. same thing here, this is what you are going to get. I'm not going to write it down here. You know, you go through the same thing. You're going to have 1, no third, no 9, no 15. You're going to have 1, 5, 7, 11, 13. If you calculate those things, you know, what you're going to get for your current IPHD, if you calculate those ones, you're going to get to 6.6%. Did I get it? How much improved? 10%. Just getting up the third harmonics, we got 10% there. So, can somebody tell me if now if I want to eliminate 8, you get rid of the third, let me tell you the numbers here, for example. If you do this one, again, the rest is going to be untouched. You know, the V5 is going to say the 25.5, and the V7 is the table you have. Those ones are not going to change, you know, because we actually brought up the DC. If you look at it, I would just get rid of the third harmonics, I improved 10% in my current PhD. Can I not take both third and fifth? Because fifth is the next one, right? Can I do that? Both of them?
You have to change the alpha. So
Alpha? No, see, based on this one, I can put only one of them here, right?
Use the resulting signal, and then we run that same process again, but with a higher frequency at the very beginning. So we should be able to do it.
How did I get rid of the third harmonic here?
You made close out of alpha
Alpha,
zero.
I select alpha, a number, right? The right number. So, if I'm going to get rid of the fifth harmonic, I should select different alpha, right?
Yes, but using this resulting signal, right? We use the same process again. But for the VDC, we have to, in the very first time we do it, we have to get a high VDC, right? Because as we keep
Yeah.
doing this,
No, but my point is, to get rid of the third harmonic, I have to have a 30 degree. To get rid of the fifth harmonic, I don't know, maybe I should have a 20 degree, for example, right? Because, so both of them, they cannot happen. Alpha either is 30, either is 20, right?
Yeah.
So what should I do?
The output is the input for another one?
For another, what does it mean?
The same thing?
No.
No.
No, I'm saying, I don't know what's the number, but let's say for eliminating a fifth harmonics, you need a 20 degree, for example. How about if I have an alpha and beta? Right? So there are two, I want to get rid of two, right? I should have two parameters to control, right? Now, this is a little bit more advanced harmonic elimination. If you are going to do that one, you need to have chopping. So I'm going to give you the homework to you guys. You know, you can go. You know, look at here. For example, how about this one? If I have a waveform like this, and this is a half a cycle. Now see, I have one here and one here, right? This is symmetry. You know, you cannot counter this one, right? Like here, I have one alpha here. I cannot say I have another one here. These are symmetry, right? So basically, I have one here and one here, right? And basically, the other one is going to be like this. The other side is going to be like this. See how nice it is? S2 is 4, right? If I want to have a VDC here, these two should be on, right? Let's put it here S1, S4, right? Now, if I want to have it here, which one should be on? 2 and 3, right? There's 2 and 3. So, let me see. We have S1, S4, and we have 0 voltages. So, even the way I'm going to have the minimum switch, minimum transition, see? S1, S4, right? To have the 0 voltage here. either I could have a S2, S4, or I could have a S1, S3, right? But I'll go with the S3. Why I went to go with the S3? Because see here what I need S2, S3, right? I'll turn on this one and this one on. Most of them they are on. So for next time I have only one change. I'm not going to. I don't need to change it. This is symmetrical, right? Now let's go plot this one to see how it's going to be. I'm going to put it right under here. And only I plot S1 and S3, right? Because the other two, we know S4, how much is S4? S2 complement is S1, right? And if this is a S3, S4 complement also is S3, right? If I know S1 and S3, the other two also they are known, right? Based on what is said here, so S1 is going to be on this one, right? S1 is this one. So how about S3? Yes, this one is going to be. Yes, I want to make sure it should be 180 degrees. Let me make sure here. This one is going to be here. S3, S3.
Shouldn't that 3 be from earlier? Shouldn't it start from earlier?
Just hold on, give me a second. It should cover 180 degrees. 180 degrees. This is a 180 degree, and this is 180. This is correct. It's going to be 180 degree, right? Now, oh, this one is start from here. This is 180 degree, and this is 180. Right? So see, why is 100 degrees? I know from this point to this point, how much is it? It's a half a circle, right? 180 degrees. So this is alpha, right? So if I come alpha degree this way, I go alpha degree this way, it still is 180 degree, right? And you can see S1, S1, right? 180 degree. The same thing here for S3. You can go for S3 here to here. This is the switching pattern for this one. 180 degree, 180 degree. If you send this one to your gates, you're going to see that voltage out in your reverse. They call this one switching pattern. They call this one switching. This is very simple. Now go think about this one. To do this one, it will be more complicated, right? More complicated. So this is a harmonic elimination we talked about. Okay. Now we want to talk about a little bit more of this is traditional harmonic elimination. You calculate those alpha, beta. For example, if I want to eliminate 3 harmonics, 3, 5th, and 7th. How many I need? 3 parameters to control, right? Alpha 1, alpha 2, alpha 3. I don't give that one in exam to you. Why? No, it's not too hard. When you solve it for 2 or 3 at home, you see the equations are non-linear. So to solve it is not easy, and you know my style. I'm not going to give something crazy in the exam. You know, the calculation should be simple, right? So, but you know, if I tell you can bring your computer, you know, so means that maybe I'll bring you something you know, that you can do whatever you want.
So at the very beginning, we use a perfect square wave. Right. Then we shift it a little bit, make this a little bit more like a sound wave.
We did this one.
Yeah.
That was
why we do it again, make it more like a sound wave.
This one.
Instead of doing this, we make it like another. Make it the center a little bit more weighting. It's going to help.
We did here.
Yeah, let's make it again.
You mean like this?
No. On top of that, make it. And
oh, you put another one here?
Yes. So it can help.
No, that's very nice. You know, that's I like it. You know, but how are you gonna do that?
Use 2 DC bus and more switch to control like.
Yeah, they call it multi-level inverter. You can do this one. They call it multi-level inverter. That's what when I said we have a neutral point balancing and those kind of things. See here only I have one VDC. But if I have a neutral point here, see right now I have only one parameter, it's the VDC. There I can go up, down, or in this case 0, right? What if I have a VDC over 2? I could have a VDC, VDC over 2, VDC, think about it, what levels I could have? if I have a half of this voltage available here in the neutral point, right? VDC. I could have, these are the level I have. VDC over 2, right? The next level I have, how much is it? VDC, right? Here, and I could have 0 also. This is better. They call it multi-level converter. We'll talk about this one a little bit. Not multi-level, but when we talk about a 3-phase inverter, we'll talk about this one a little. You see this waveform later, a little bit later, maybe next week.
When it comes to switching loss, which one has?
Multi-level converter, see, there are 2 ways. Either you can go this way, build it this way, or this way. This way is more switching, this way is a more level, right? Always there's a compromise here. Which one is better? You want to have more level, more levels, have this pane here to balance this one, or you want to go with the higher switching and deal with a higher loss and those kind of things. These are designed for me. Every project is different. You select one with this one with that one. Usually when it's very high power, high voltage, you go toward the multi-level converters. But even nowadays, for small PVs, they're going to multi-level converters because it's going to give you much better efficiency. There's less switching. Maybe 5 years ago, because we didn't have that kind. This one was expensive to go that way. Now they're reducing the price. With the technology advancing, they're going more toward the multi-level. Because think about it. If you build this one, maybe this is good enough, right? Maybe 1, 2, 3. Right? This one you don't need chop anymore, right? This is pretty good. It has a pretty good harmonic spectrum. You can make this one a little bit wider here in the middle. That's good. I mean, you switch maybe 5 times, 6 times.
For how you balance?
Yeah. As I said, there's a problem with everything. But I'm saying this is very good because you get a very good harmonic spectrum out of this one with a very, very low switching. Very, very low switching. We'll talk a little bit more about that. We can offer 10 courses in power electronics, and still there is more material to cover, you know what I'm saying? But we try to cover the basic here, and the rest is going to be you guys, you go study it yourself, start to work on something, come up with a new circuits, topologies, and those kind of things. I want to finish this single phase today, There. Now we're going to do bipolar switch. This is the PW. By the way, we came to the PW. As soon as you see this one, start to chop those signals. We call it pulse width modulation. But again, we have the single phase inverter. Let's go back to the same thing we had before. Half bridge. Now, I told you to go with a harmonic elimination to calculate those alpha, beta, gamma, those things to get rid of the 3rd harmonic, 5th harmonic, 7th harmonics, or we can do this one. They call it sine PW. Or they call it sine delta PW. What's the word they call it delta? Me, at the end of the day, I want to have a sine waveform here. Right? That's a perfect ideal case for me to have a sine waveform, at the output, right? This is what I want to have at output, right? Now, I need to start to chop this voltage here. Chop, I mean this, right? If I compare this one with okay? I call this one control waveform, V control, or V cone, I call it just VCON. I call this one VQR, or carrier waveform. Now, what I will do is like, I said, okay, my switching function, for example, for this switch, and the other one should be complementary of this one, right? This is for S1. I'll say if V control is more than VQRI, S1 is 1. If V control is less than VQRI, S1 is 0. This is switching pattern, like the one I put it here, right? So basically, if you plug it here, so from here, actually there is a one notch here, no, but my waveform is not very accurate here. So basically, if you look at it, it's going to be like this. You're going to have one on here, it's actually one off here, sorry. One, because during this time, this is the control, right? And this is the QRI. Control is less than this one. So less than the QRI, so it's going to be like this. And up to here, they're going to be on. Again here, they're going to be off. Up to here, they're going to be on. This one should be very symmetric, you know. I haven't plotted it very nicely, you know. That's the reason you see this way. And we see it here, and again it's going to be on. Sorry. Oh, let me see. I don't think we see here as well. So it's going to be like this. Here. And here. These are signals I'm going to see. Right? I compare this. This one doesn't look good, but if you go put this in piecing case together, you're going to see how good it's going to look like, you know. Now, how much is the VO? How much is the VO? If S1 is on, how much is it? VDC over 2, right? It's going to be like this. If S2 is on,
Negative VDC.
negative VDC. Right? Positive VDC. Then like this. They call it pulse width modulation. Now, this is very slow. So usually when you do this simulation, if you plug these two on top of each other, you're not going to see the sine wave because the frequency of this one maybe is a 200, 300, 500 times of this one. So it's going to, this one's going to be very, very, very narrow. You know what I'm saying? So try doing the simulation. We'll do that one a little bit later. Maybe next class, you know, I run one simulation here. I'll show you this case. But this is how the switches are going to turn on, turn off. They call it sine PWM because you are using this sine waveform as a base, right? They call it sine PW. That's the reason it's called sine PW. Now, what is the bipolar? This is for the half bridge. But what is the bipolar PW? When you say bipolar switching, bipolar is going to go back to, two things I need to introduce here before we go. There is a two parameters we need to define, MF and MA. MF, they call it frequency modulation, and MA, they call it modulation index. MF is the relation between this VTRI, frequency of this VTRI and V control. So basically, MF is going to be F of the TRI over F of the control. Usually it's a big number. The higher the better. Harmonics, not switching. Because the higher MF means you are switching faster. You are going to have more switching loss. The lower MF means we have less, switching, less loss, but the harmonic is going to be more. What is MA? Look at here. There's a maximum here and maximum here, right? MA is defined V control hat, maximum of the V control over the maximum of VTRI. MA is called modulation index. It is the maximum of the sine waveform divided by maximum of the triangular wave. Look at it here. I can change this one to have it like this. That's another. I'm going to change the maximum of V control to be like this. What is going to happen? During this time, they're not going to cross each other, right? Because this one is much bigger than this one, right? They call this case up to MA is 1. 1 means both of them they have the same maximum, right? And still they're going to cross each other, right? If MA is more than 1, they call it overmodulation. They call it overmodulation. We'll talk about this one a little later more. We don't like overmodulation because the system is going to get some harmonics. It's got to get some harmonics. But if we have to, at some cases, we have to go. If MA is more than 1, they call it overmodulation. If MA is less than 1, they call it linear modulation. Linear modulation. So if they are talking about the linear modulation, you need to start to do some simulation to get better feeling about this, what we are talking about here. I'll show you some simulation next class. I bring some cases we can look at, so make sense better. But so change, and for example, I'll change MA. I'll run a simulation. You can see I'll go over modulation, under linear modulation. You can see the effect on the output voltage. It's extremely difficult to draw those things here. But we'll go over it, next class. I'll give you some slides after the class, the discussion. I'm going to go over those kind of things. I'm going to show you some of those simulation cases. Now, what is important for us under the linear modulation? I want to know if I have this MA, MF, I have VDC. What is important for me is a V1, right? I need to find a relation between the VDC, MA, and V1. V1 is a fundamental harmonics, right? Because that way I can select this one. Hey, if I select 0.8 MA, I don't know this much VDC, I'm going to get 110 volts out. We need to derive those equations to see how this thing is going to work. We're over the time. I don't want to go down. It's going to take time, and there's a little bit math involved with that. But keep this one in mind. This one was a sine PWM for the half bridge. I'm going to continue with the same thing, MA, MF, modulation. Next class, I'm going to go to the full bridge with a bipolar. I didn't talk about the bipolar. Bipolar basically has another waveform here, like this. We'll talk about that one in the next class, the bipolar. And we go over the harmonics. The same example we solved today. We solved it quickly for this case to see how much is going to improve your GS. I can tell you, I have the numbers here, just to tell you, if when we do this example here, the voltage THC looks like it's going to be 8% from what we have. But we'll go over the example in the next class.